Okay, good afternoon. I think we'll start the afternoon session now. And yesterday and this morning, we're discussing parallel programming within the message passing paradigm, and particularly with MPI. Now we move to a bit different way to parallelize programs and start with shared memory parallelization using threads and OpenMP. And then in the latter part of afternoon lecture, we see how to combine the shared memory parallelization with OpenMP to the message passing approach with MPI. So let's start from some very basic concepts and differences we have here. So in MPI execution model, the parallel program is launched as a set of independent processes which are kind of their own execution units, have their own state information, and probably the most important fact distinguishing threads and processes is that each process has its own address space. And in practice that means that one process cannot directly access the memory of another process. And in MPI, in order to actually get the data from other process or get data to other processes, one sends and receives messages. Thread, on the other hand, is in a way more lightweight construct. So when using threading, we always start with the single process, and then at some point, execution time of the process, launch multiple threads. And whereas when doing the parallel programming with MPI, one always creates all the process, or practically always. There are in principle possible to create processes during the execution of programming MPI, but it's not very often used fact. All the processes are created when the parallel program starts, and the processes are also destroyed when the parallel program ends. Threads, instead, they might be that, okay, they are started at some point. So one launches here for in this example 4 threads. At some point, the threads join back together, and a little bit later on, one can launch again new threads, sometimes even different number of threads. And as I said, that important, yes?
If you have a problem with a loop, you have a repetition of something that all the processes do together, and then processes that only one thread does. How would you go about parallelizing it? Would you keep the threads all the time, or would you fork and unfork them every loop?
It really depends on what kind of loop and what other things they are doing in the program. In practice, what I think that, for example, most OpenMP runtimes do that there is some sort of thread pool which is created when you start the program, or at least when you first launch the threads. So the thread creation and destruction overhead is maybe not that drastic. But sort of rule of thumb, we'll discuss maybe a bit more later on, is that when you are using OpenMP and when you're using threading, it's good to have as coarse-grained parallelism as possible, and that also means that it's good to have threads launched and killed as few times as possible. But it really depends a bit at what's going on between the loops and how much computational time is spent in the loops. If really everything 95% of time is just spent on the loops and something else in between, it probably doesn't make big difference whether you launch threads again and destroy them in between. So I meant that the distinguish thing between process and thread is that processes have their own address space, while all the threads, in principle, they share the same address space. And that also means that because threads share the same address space, same memory, the communication between threads is possible just by accessing variables in the same shared memory. In MPI, one has to send and receive messages. Here, no messages are needed at all necessarily. It's just that one thread reads some memory location, which other thread has maybe been modifying a bit later on.
So if I pass a pointer to another thread, then it will be able to use the pointer because they're using the same memory?
If you have declared, let's say, a pointer here, and then you launch threads, all the threads will see the same pointer and same memory location.
I pointer and then I redirected it. And then
If you redirect it, yeah, other...
just one of the... I invoked it.
Yeah.
Just one of the threads, I redirected it, and then I passed the value of the pointer to another thread. Will the second thread be able to use to retrieve the information from that address?
In principle, yes. It depends a little bit. We discuss a bit more when we see how to define parallel regions and data visibility, that in what situations and what variables threads can share and so on. But in principle, that's what's going on there. So the distinction between threads and process to keep in mind is that threads are something lightweight. You can create and destroy them on the fly, in principle, and that with processes you cannot access the memory of other process, while with threads the memory is shared between them. There are actually different possibilities for doing threading, thread-based programming, and there are so-called POSIX threads, P threads, which is one sort of standard for working with threads. OpenMP is other way, and OpenMP is in principle it's a standard, and it's in principle a collection of compiler directives, library routines, and some environment variables that can be used in order to make serial code multi-threaded and parallel using shared memory parallelism. The current most up-to-date version of OpenMP is 4.0, a little bit less than a year old. Most compilers at the moment actually support version 3 or 3.1 of OpenMP.
When you say compilers, you mean GCC?
GCC, Intel CC,
Yeah.
Cray CC.
But you mean the standard compiler, not some MPI something?
Well, MPI compilers, basically if you use MPI CC, that's normally just wrapper around some other compiler, adding include and library flags and so on. So it's using, for example, in Euclid, it's just using GCC for the actual compilation. OpenMP supports Fortran 77 and probably nowadays also Fortran 2003 and so on, and also C and C++. As OpenMP and practically any thread-based approach relies on shared memory model, shared memory programming. That means that there has to be also shared memory in the actual physical machine. And that also limits a bit the usability of pure OpenMP. So you can run it only in a single shared memory machine in your own workstation or in node cluster, but you cannot really run it on big distributed supercomputer. And you cannot typically scale OpenMP programs to thousands of CPU cores because there are no such shared memory machines. On the other hand, OpenMP makes the parallelization of code in principle very easy. You just add some directives, as we'll see, to the code. And it's also something that it's very easy to work on in sort of sequential fashion that you first parallelize one piece of code, one part of code, couple of loops, then you maybe profile a bit more and see that, okay, there are also some other parts that need working, so you can be parallelizing the program piece by piece. So you get some speed up with quite limited amount of time. And you can have a coexisting serial and OpenMP programs. That's straightforward. And even if you wouldn't be using OpenMP to get really high scale, a hybrid programming where you combine MPI and OpenMP, which we'll discuss later on today, is something that it will be also very useful. Naturally, if you want to do hybrid OpenMP, MPI programming, first you need to know both MPI and OpenMP. There are in principle 3 different components in OpenMP. First, we have some compiler directives and constructs. And they are just giving the compiler some hints that how to parallelize different regions in code. Where to launch threads, where to destroy threads, where to do some work sharing. Then there are some runtime library routines, number of useful routines or routines at all, it's quite small. But basically there are functions you can use for querying the number of threads currently on the run, and also what's the sort of ID of each thread. And then there are also some environment variables which one can use, for example, for specifying the number of threads and so on. The way these compiler directives work is that they, in Fortran code, if you're not compiling it as OpenMP, they look like actually comments to code. While C, you use them as a sort of pragma-like syntax. There's some pragma something, which is also something that the compiler will ignore when you're not actually doing an OpenMP code. For library routines, it's possible to do, if you want to use them in serial code, it's possible to do conditional compilation, we'll see. So these sentinels, which define the OpenMP directives, say they have a little bit different form in C and Fortran. So in C, you start lines by pragma, OMP, and then you give the actual directive what compiler should do. In Fortran, is there actually someone still using Fortran 77 and fixed form? Oh, good. Okay. Lucky of you. Lucky of you. So you can then more or less ignore this one. So in Fortran free form, these sentinels, as I said, they appear like comments. So you have the sort of comment character, then the $, and then OMP. And in C, in principle, these OMP pragmas, they always relate to some code block, in principle defined by the curly braces, while Fortran, you have some sort of start and end directives, so that, okay, start something really OpenMP related and then end something OpenMP related. As mentioned, the sort of serial and threaded code, they can coexist very easily. And typically by default, most compilers, they will just compile the serial version. And you have to give some specific compiler flag in order to do the OpenMP threaded version. And for you, probably the most important is this GNU's -f OpenMP, which you need to include to get the threaded program. As mentioned, it's possible to include some sort of facilities library routines in the code which you want to also run in serial manner. When you compile with OpenMP switched on, I think the OpenMP standard says that this sort of preprocessor macro gets defined, and you can automatic fashion say that, okay, if I'm running in OpenMP mode, do something here. That's especially if you call some library routines. If not, do something else. Okay, let's look very simple, or make very simple OpenMP program, OpenMP hello, to start with. Let's make it in Fortran this time. We call it hello, and what it does, it just writes hello and end program. So this would be the normal serial program. And now, in order to make this OpenMP program, we add here now some directives. So OMP, and discuss that a bit later on in a bit more detail. We want to launch some threads here. So we define an OMP parallel region here, and then we also want to end that one. So that's now everything we need to do to make this simple program parallel with OMP. Let's try to compile that. Okay, compiles nicely. If we run that, okay, we get single hello. That was our normal serial program. Let's now make this OpenMP program. So we add this -f OpenMP here to G-Fortran, compiles, and now if we run that, we actually see that by default, this machine here has 4 CPU cores, and it has used all these or created thread for all of the CPU cores. So we actually get 4 times the hello here.
It automatically detects how many cores you have in your machine and necessarily occupies all of them?
You can specify via environment variables actually how many threads you want to use, but at least this GNU runtime now by default seems to be using number of threads equivalent to the number of CPU cores. I can specify here that, okay, let's use only 1 thread, or I could also say that let's use 8 threads. It probably wouldn't make that much sense if I have only 4 CPU cores, but that's something you can specify here. Yes?
In this specific example, can you maybe say a couple of words about CPU cores versus threads, CPU threads?
I would say that the CPU core is the sort of physical unit that can perform some computations. And thread in general is something more abstract, something that one can say that operating system launches number of threads.
If you have a CPU socket
yeah,
having 2 cores,
yeah,
each dual threaded, what does it mean?
That basically means then there are some CPUs that are able to run possibly multiple hardware threads at the same time. It also depends a bit type of operations. So for example, some recent Intel CPUs, for some operations, the CPU core itself can do some overlapping of the operations. So it might be that it can do almost 2 instructions at the same time. Not quite 2 at the same time, maybe for very specific operations, but that's I think what typically meant that, okay, some CPU or CPU core can run multiple hardware threads.
Assuming I have each of them has two.
Yeah.
Is there any rule of which parallelism would work best, or should I just benchmark and try which gives the best performance?
Yeah, only thing I think you can do is you can try. It really depends on the actual CPUs. It depends on what application you have. So, but of course, with if you really want to, for example, see that how many OpenMP threads is good, it's really easy to just try to run it with different number of threads and measure the execution time. So as you see, it's in principle it's very easy to get first sort of parallel program with OpenMP constructed. Here you can actually see one of the library routines, so that each thread here can also print what sort of the ID. Okay, so you already saw the sort of most important and most basic OpenMP construct, and that was the parallel directive that creates a parallel region. And basically it just means that, okay, at this point, when we have the parallel, launch some number of threads. System might have, as you see, have some default at how many threads are by default used. This seems to have 4, but with the environment variables, you can specify that use 1, 2, or 8. In any case, when we have this, or when we start the parallel region here, some threads get launched. In principle, prior to that, there is only single thread, so-called master thread, and after that, there are master thread and then some slave threads. In MPI, all the MP ranks in principle, they are just equal. It's just common program practice that the rank 0 does something a bit differently than the others. In principle, it could be always just the last rank at time. It just has been convinced that it's rank 0. In OpenMP, there are some constructs that actually make some difference, that whether thread is the master thread or one of the slaves. In Fortran, the parallel region is ended by OMP end parallel directive. In C, it would be just OMP parallel and then some block of code. Typically, you would have a curly braces here to define the block that should be defined or should contain the parallel region. At the end of this parallel region, there is always sort of barrier. So before the threads are destroyed and one continues with single thread, one waits in principle as long that all threads have reached this point, and also all the sort of shared data will be synchronized at this point. As the threads share the address space, the sort of way to communicate is using shared variables. However, there are many cases that they actually, within the parallel region, they still need some private workspace. So they want to update some value, and if all the threads would just update the same variable, same value, that would make the program work incorrect way. For example, if you think we are making a for loop, and we have the loop index, and we have a parallel region over this loop, and naturally we would like that each thread works only with specific loop indices and not with all of them. Now, what might happen if we didn't do any precautions that, okay, first thread updates the loop index and tries to do something. Next thread goes into the loop, updates the loop index, but before it starts to do something with the loop index, it might be that third thread will actually already be updating that one. So for that reason, to sort of get so that one can get rid of these kind of race conditions. One can make also directives that what should be the visibility of different variables within the parallel region. Should they be all shared between all the threads, or should they be private to the thread? By default, most variables they are shared. Global variables they are always shared. Also, any static or file scope variables in C are shared. In Fortran, module variables, and in both languages, dynamically allocated variables they are shared. By default, private variables are those that are declared within a block, automatic variables within a block, and also if there are some sort of internal variables in function that will be called in parallel region, they will be always also be private. When creating the parallel region, one can sort of add these data sharing attributes there and list variables that should have a definite visibility among the threads. So one option is that, okay, we make the variables private. So all the variables listed here in parentheses, when one enters the parallel region, they will have undefined initial value, and they will be stored in sort of private stack of each thread. And when you go out from the parallel region, these variables, once again, they don't have any well-defined value. In some cases, it might be that actually when you enter the parallel region, you would like that, okay, the variable actually has some well-defined value, some initial value provided. Then it's possible to use this first private clause. It's otherwise the same, but for each thread, the variable has initial value that is same as in the sort of original object, original variable outside the parallel region. As mentioned, the private variables, when you go out from the parallel region, they don't have well-defined value. By declaring private with the last private, it means that the thread that performs the last parallel iteration step or section, or in principle the thread that at last exits the parallel region, will copy its value to the original object. This is not so well defined as, for example, in the first private, where it's always the value that the sort of master thread had before entering the parallel region. And it's also possible to declare variables as shared, and this means then that all the variables can write to read to. And practically, in most cases, one wouldn't need explicitly to declare variables shared, but it's in many cases good because they are by default shared. But in many cases, it might be good programming practice to explicitly say that, okay, whether variable is shared or private. And it's actually possible to sort of put some default for variables that and it actually, this is sometimes useful for debugging. One can put default none, which means that each variable has to be manually declared to be either private or default shared.
Question?
Yes?
Can you have the same variable as first private and last private, meaning that you get the value from outside, work with it, and then return it?
Yeah, I think it should work. Yeah.
Okay, thanks.
here is a simple example how different type of declared variables would be shared or not. So by default, okay, this would be file scope variable. This would be global variable within the main routine. So this would be shared within this parallel region here between all threads. On the other hand, when we call this function here, the sort of internal variables here, that would be private for each thread. On the other hand, because this is now static here, that would be shared. And also this is file scope variable, and that way would be shared between all threads. Any question about creating the parallel regions and data visibility at this point? That's, of course, not... yes?
Regarding the extern, you can use thread private to define a variable or a memory region that can be used that is private to each thread.
One could have here OpenMP parallel and then private and, for example, A. And after that, the variable would be made private to each thread within this region.
Okay, but
And then I think if one would be modifying the array here within these two things, it would be local to the thread. So other thread wouldn't be modifying the values of other threads. Yes?
So what happens with this private array double when the parallel region ends?
This one here.
Yeah.
That's actually the same thing, that even if there wouldn't be any sort of parallel region here, when one enters this function here, I mean, this is sort of function internal automatic variable. When we enter the function, this gets sort of allocated from stack, and when the function ends, it will be vanishing. And same happens here now, even though similar while it's in the parallel region, it's just that it's also private to each thread, so that modifications that one thread does to this array are not visible to others. Okay, so that's sort of how we can launch threads and declare some data to be private or shared between threads. But of course, in order to really benefit from threading, from parallelization, we would like that different threads would do different things. And for that, OpenMP provides directives for declaring that how certain work should be shared between threads. In principle, the parallel region, it always means that all the threads execute the same program code. So it's this single program, multiple data approach. Of course, if you query the thread ID of the different threads, you can have if statements very similar to MPI case, where each MPI process executes the same program code, but based on the values of the rank, you can do different things. One can actually do this kind of manually, assign work to different threads based on thread ID. But OpenMP provides for some common use cases ready-to-use directives. And probably the most often used construct is that, okay, we have some for or do loops, and we want that different threads execute different part of the loop. We discussed a bit also that how we can make a single or only a single thread perform some work, and there are also this. In OpenMP 3, it's also possible to do sort of task parallelization, but we won't be discussing that in this lecture. Okay, loop construct is very simple. So inside the parallel region, just before some loop, we put the directive there that OMP do in Fortran or OMP4 in C. Quite often it might be also that, especially if we are always, there was this question that whether one should launch and destroy threads for each for loop. Especially for if one does this, it's possible to combine the parallel and do and for directives, so that just before for loop we start the parallel region and at the same time instruct the compiler that work on the loop should be divided between threads. And the outermost loop index is private by default, but the innermost loop indices are not. I think there is actually some difference between Fortran and C that how these innermost loop indices are treated, but I think that in most cases it's safest to put them all private explicitly. There are some restrictions that, I mean, what kind of loop constructs one can use in C code. Now, in principle, the C's loop construct is quite flexible, but only a specific subset is supported by OpenMP. So this has to be the standard initialize some value, variable to value, do some of the basic comparison, and then do the increments by standard amount. It can be other than one, but it has to be some sort of constant amount. Okay, let's talk a bit about how to synchronize between threads and what kind of issues one has to take into account there. Here would be sort of very simple parallel do loop in Fortran, where we just this would be just a dot product of two vectors x and y. So we launch some threads here and put the loop variable here as private. It would be by default, but it's still good practice to explicitly write it down and say that, okay, these vectors, we want that each thread can access the vectors, not necessarily all the elements, but and also this should be the loop index here. Every thread should know that, okay, what's sort of last one here. And we also put this sort of sum here as a shared variable. And now do this parallel do construct here. What the compiler does at this point, that okay, let's create some threads and let's distribute the work of these n different iterations to different threads. Problem here is now that okay, it is ASAM here. That's now shared, and what we have here is so-called race condition, meaning that it might be that one thread is actually writing to this variable at the same time as other one is reading from it. And because we are using the variable also in right-hand side here, the order which this happens will actually affect the results. And at the end, the result we get out from this will be random, depending just at which order the threads will be updating the sum here. And we need something to actually control that, how this is done, so that we avoid this race condition and get the correct result. These type of operations are so common that for this kind of reductions, OpenMP directly provides some actually way to deal with that. And the way to do that is use the reduction clause, where we can put some different operator here. I think in the next slide I should have what are all the possible operations available in OpenMP. In our case, it would be natural that it would be the addition we want to do here. And then there will be the sort of variable name that we want to do the reduction for. There actually could be several variables. And what now happens here is that when we enter this parallel construct, there will be sort of private variable created beneath the scenes for each thread. It will be initialized to some initial value depending operator here. For addition, that would be 0. Each thread would perform the sort of work, update the value of this private variable, which doesn't actually show up to the user program. And when one ends the parallel region or this parallel construct where the reduction is applied, the values from each thread are aggregated to the master thread and summed together. Yes?
The operator, can you just choose from a limited set that OpenMP offers, or can you write your own?
Just this limited set that OpenMP offers. So for Run, you can have also some logical operators, like this one. These are probably the most common ones.
So in reduction, you're also limited to primitive types.
Yes, that's true. So we can have an additions with initial value of 0, subtractions, and multiplications. In this case, the initial value will be 1. But in C, for example, there is no maximum or minimum. So it's a bit different than MPI reduce, where you have a little bit more selection of what operators use. And in MPI, you can actually also, I think, define your own reduction operators. So now this same program could be done with the reduction clause here for the ASUM, and with this construct, it would now work in correct fashion, not in random fashion, depending which order the threads enter the loop or execute the statements in the loop. There are sometimes also cases where part of parallel region should be executed only by master thread or just by single thread or any single thread, or sometimes just by single thread at a time. And in principle, the reduction could also be done in this manner, so that each thread would have updated the ASUM one thread at a time. Of course, you would lose all the sort of parallelism because it would be just serializing that. And there are some clauses that OpenMP provides for controlling execution. Barrier is the sort of most simple synchronization control. And just like MBA barrier means that the execution of the program continues only after all the processes have reached this point. In OpenMP, this means that execution continues only after all the threads have reached that point. There is implicit barrier at the end of parallel do, and in principle this barrier cannot be inside any if statements, so there will be deadlock if not all the threads enter the barrier. Master is something where one can control that there is some code block region within your parallel region that should be executed only by the master thread. And as I said, in OpenMP, not all threads are equal, and this is one construct where the so-called master thread behaves a little bit different. So thread with thread ID 0, it's always the master. And if there is some region in code designated by this master, it will be executed only by this one particular thread. It's also possible that it can be, it doesn't need to be master. It's enough that it's any thread, it's just that it has to be only single thread that executes a region. That can be done by single statement, and in principle that means that the one thread that first reaches this point of code will continue the execution, while the others will wait at the end of this single region. The difference, one difference between master and single is that at the end of the single region there is always implicit barrier, while in master there is no barrier, so other threads can proceed on doing whatever they want while the master is doing something within the master region. Yes?
So if I use master pragma and
Yeah.
the barrier, is it equivalent to single?
Almost. Only difference is that still it can be some other threads here than the thread 0. Here it's always the sort of thread 0. Here it can be any of that, but the flow of the program would be more or less the same in both cases. There can be only some parts that will be executed by multiple threads, but only one thread at a time. And these are the critical sections. It's also possible to give a name then, and in that way it's possible to have sort of different critical sections, so that critical sections with different name can be executed by two threads at the same time, but critical sections with the same name, they can be executed only by one thread at a time. And sometimes, the sort of final execution control I have here is that sometimes one doesn't need to make a barrier, so it doesn't need to synchronize the execution of all the threads. It's just that the sort of memory that each thread shares is consistent, and that can be done by flush. Especially with, modern processors, they have lots of different level of caches. So in many cases, it might be that thread works with variables in a cache, and other thread might somehow be working with the same variable, but which is still in the main memory, and that would result that even though the both threads are sort of about to work with the same variable, because of cache effects, they would have a different view of the variable. And by having this flush statement can be used to force that, let's do some synchronizations for the memory and caches and make sure that cache effects are not making any harm there.
Question?
Yes?
The flash command happens once, or once for every thread that is passing this pragma?
I think that threads wait at this point until the sort of I don't think there is in principle barrier there. So it might be that variable some thread hasn't, for example, attached any data that it's in the local or in the global memory. That means that it don't need to sort of update its own changes. It might be in cache to the main memory, so it can just continue executing there. But some other thread might have that it had read some variable or some array from main memory. It will be residing in cache, and it can go on after this point only after it has sort of made sure that the memory is coherent. There is implicit flush at the end of barriers and critical sections. And in some hardware platforms, there are sort of atomic updates, meaning that you can do read and write of some memory location, but in principle with the single computer instructions. And it's possible to also have this kind of construct in OpenMP, but it's strictly limited to update just a single value, and it cannot be applied to code blocks. So it's just one line that follows the atomic directive that can be, or it applies to. Here's an example of using doing the reduction, not with the reduction clause, but with using these critical sections. We create the private variable here for the partial sums. So the actual partial sums here can be done in parallel by all the threads. They will be updating only the on private variables. And at the end of this do loop here, we have a critical section where the sort of global sum will be updated by all the threads. So this will now be executed only one thread at a time, so there won't be any race condition, and a sum at the end of this parallel region will contain the correct result. Here is an example about using the master and single threads. We might do some parallelization or initialization here only by the master. Maybe some other initialization by other threads there. Then we do some computation here, and we might want to do output only from a single thread there. Here is how you can update a global variable, once again using a critical section. So this is in principle how you can do the reduction for maximum value. And once again we make some local maximum here, private value. We want to start from 0, so it now made first private here. We do the sort of local maximum here, and then in a critical section we looked at which one of the local maximums is actually the global maximum. Yes?
So the OMP critical is like still going in parallel according to the number of threads?
It's not going in a parallel way that let's say we have 4 threads executing here. When we reach this point, or when any of the threads reach this point, it can execute this statement here only if no other thread is executing that. So the other threads all the threads will execute that.
But in order, not at the same time?
Not at the same time, just one at a time. In a random order, but only one at a time.
Okay, so it's actually executed as the number of threads?
Yes.
Okay.
And way to do it this way that this is the large loop, so this is the sort of principle. One could also put a critical section here, but then you wouldn't have any parallelism because only one thread would be executing that. That way, most of the work we can do parallel here, and only this final sort of reduction by serial sort of operations. There are some ways to interact with the environment. You already seen that, okay, it's by environment variables. It's possible to set the number of threads that we want to use for execution. We haven't touched things as how to do the scheduling for work sharing clauses. There are different possible ways to do that, whether one assigns a constant chunk to each thread or whether one tries to do some sort of dynamic balancing there. This is actually something that can be shared by environment variables also. Probably the most important one of environment variables is really this OMP num threads, but there are a few others that the standard also defines. The runtime functions, so the OpenMP API, it consists of, in C we have the header file, and in Fortran we have a module, OMP-lib. There are probably around a dozen different functions there, but the two most useful ones, in my opinion, are OMP get num threads, which, as name implies, gives just the number of threads within the parallel region. So if you call this outside parallel region, it will always return 1. But when you call it inside the parallel region, it returns how many threads are running at this point. And OMP get thread num gives then naturally the ID of that particular thread. If you call that outside parallel region, it always returns 0 for the master thread, but within the parallel region, each thread will have a different value returned. Here would be sort of simple example of parallelizing loop with library functions. As we don't want that, okay, other threads modify the value, for this one it probably wouldn't be that drastic because all the threads will have the same value there, but thread ID naturally has to be made private here. And one way without any sort of OMP do or OMP4 clause would be that actually now the loop variable here would start from thread ID and it would be incremented in terms of number of threads. So very much that you might parallelize this kind of construct using MPI. So it's similar type of parallelization is possible also with OpenMP. Of course, in most cases, it's more convenient to let the compiler do the job and do the parallelization there.
If you're porting code from MPI,
then it might be that it's sometimes it's something a little bit more tricky than simple loop here. So there are some things that might be easy to parallelize by playing around with the number of threads and thread ID. There were already this question that, okay, how one should actually do the OpenMP program. These are not any strict rules, but sort of best practices, rules of thumbs that in many cases have turned out to be good. One is to really maximize the parallel regions, so not launch and destroy threads every now and then. Try to parallelize always the outermost loops, if possible. It's also actually possible to parallelize over multiple loops. Also, small arrays might be useful to make private, which reduce the access to the shared data, and sometimes that can give you better practical memory bandwidth of using small arrays as private.
Again, sorry. So what gives us better memory?
Sometimes declaring some small arrays as a private one, so that when the threads will be accessing the accessing to arrays, sometimes it's faster if they are private one, even though they, from programming or from the sort of logic of the algorithm, they could be made shared. Sometimes for performance point of view, they might be some benefits of making them private.
So make the shared as small as possible.
Sorry?
Make the shared variable as small as possible.
It really depends. Small here, maybe if it's an array of 10 elements, that would be small.
So you mean the size of cache and below?
Something like that, yeah.
So if you
Might be useful.
like the list of index, strings, stuff like that, keep private.
Yeah.
Then you have more, less traffic on the bus.
Yeah. Okay, there are lots of stuff in OpenMP. It's easy to get started, but it's still quite fast standard. And despite the fact that it's on surface, it's very easy to parallelize things. Getting a really very efficient parallel code with OpenMP, it still might require some effort. So I think it's time to summarize the basic OpenMP here. So OpenMP is a standard for thread-based parallelization, and it basically consists of compiler directives, runtime functions, and environment variables. As I said, it's quite easy to get started, but very efficient parallelization is non-trivial. And one drawback is naturally that it only can be used only on shared memory machines. Still, it can give some decent speed up with very modest investment of time. And naturally, for hybrid programming with MP and OpenMP, it's an important ingredient. Mainly discussed how to create parallel regions and about the data visibility and most simplest work sharing and scheduling directives here. You have any questions about OpenMP at this point? Yes?
Maybe it's a little bit related to the next session, so if it does, I will ask it again later. What would you consider best practice in the case, for example, if you have you want to make use of a lot of threaded functions that are built in, for example, MKL, and you want to use a single thread between them, and maybe you have some parallelizable work that you want to do with OpenMP.
Mm-hmm.
So going in and out of pragmas is not best practice. So you should, I don't know, include the MKL inside the OMP.
Probably in most cases you actually would need to call some MKL routine outside parallel region. Nested, it depends a bit on compilers, but it can be that you get some problems with nested parallelism. I mean, if you call, let's say, dgem inside the parallel region, what happens that, okay, you go to the parallel region and you create, let's say, 8 threads. Then you enter the dgem call there. And what, for example, MKL might do, okay, let's try to launch another 8 threads, and suddenly you would have 64 threads trying to execute the same things. So when using these sort of threaded libraries, I think in most cases you actually have to call them outside the parallel regions.
So what would be preferable, to use actually the threaded libraries, which are thread safe, or to use serial libraries inside threads?
Probably depends on the library, but for example, plus libraries are typically very, very well optimized also for threading point of view. So in most cases, I would say that it's better to use threaded library. Of course, depends a bit that if you sort of parallelism you have there, it's really sort of trivial. So instead of, let's say that for some reason you would like to do 4 relatively large matrix multiplications, then the sort of options would be that, okay, you do and they would be independent, you would do the 4 multiplications in sequential fashion. So first do the 1 matrix multiplication, use threaded MKL, then next, then next, then next. If these are really independent, it actually might be better that Contravatta say that, okay, actually launch 4 threads and then do each of these matrix multiplications at the same time. But just because of the fact that it's sort of trivially parallel, you don't have any thread synchronization or interaction for the individual multiplications. Why, if you do the matrix multiplication in threaded fashion, it won't be perfect. There will be some overhead. So, yes.
How efficient is OpenMP? Like, how big is the overhead for using just threads in C++? Is it?
Oh, I haven't done really any benchmarking, for example, with respect to pthreads. Actually, I think in GCC, if I'm not wrong, OpenMP is built on top of pthreads. So I cannot give you any direct numbers. You will get some overheads there, that's sure. But probably depends a lot on the application case that whether it's significant or not. And on the other hand, when you're using OpenMP, in principle giving the compiler opportunity to optimize also the threading a bit, depending how good the compiler is or how good you are in making well-optimized threaded code, it might change the thing that actually OpenMP is more efficient. But it might be that it's not. I mean, it depends. Okay. If there are no more questions, I think it's once again time to get your hands dirty, this time with OpenMP, and try to do some exercises on some very simple OpenMP usage. And I think if you are doing the exercise on Euclid, these instructions how to compile and run OpenMP programs should apply mostly also that case. So you need to use this -f OpenMP when compiling code. Same for GCC. And when running, you can of course try to work with see what's the sort of default number of threads used there, or just specify by yourself with the OMP nom threads environment variable.